basic signal flow and electronics. And the reason that we go through this next, we've covered sound and basic properties of sound, we've covered hearing, we've covered the way sound behaves. So now let's start talking about signal flow, because when you start recording, signals have to get from one piece of gear to the next. Acoustic sound gets transduced into an electrical format, what happens to it and how it gets manipulated and how we can make it the way we want it to sound when it comes out of the speakers finally at the end of the chain. So let's start with basic signal flow and basic electronics, because signal flow is the way that the signals travel from pieces of gear to pieces of gear, and within the piece of gear there's also signal flow, and that has to do with how the electronics inside the piece of gear handle it. And so it's always wise to have a little understanding of what actually happens inside your iPhone, what happens inside your computer, rather than you turn it on and it just doesn't come up. Something's wrong, you don't know, or you have a little understanding of what's going on inside the computer and in terms of electronics. Not that I'm going to get very technical, because I'm not, but it's good to know a little bit about the basic components of electricity, because that's really the domain that we're going to be doing our recording in and manipulating sound and signals. That'll eventually go back to the acoustic domain, but in the meantime we're going to spend a lot of time manipulating on our computer in the electrical domain. Okay, so let's go on to the next slide. A schematic, a few definitions. A schematic, in terms of an electrical description, is a precise diagram of the electrical and electronic components inside the device. It's the kind of thing that you see when you look in the back of a manual and it has all of these lines going every which way with all sorts of arrows and circles. That is what a schematic is. Now, a schematic is a very detailed view of what's going on inside of a piece of gear in terms of where the electrons flow and the signal flows. So it really deals with electron flow. And the next thing to discuss is what a block diagram is. Block diagram is the overall understanding of where the signal flows from pieces of gear to pieces of gear. So in a sense, a schematic deals with the electronics inside one piece of gear, where a block diagram deals with a whole system of gear, and it shows you where the signal flows from one piece to the next. So as a good example of what a block diagram is, let's say I set up a microphone and then I connect it to a microphone mic preamp. From the mic preamp you might go into an EQ, an equalizer, or you may go into a compressor to manipulate the signal. Then you might next go into some sort of recording device. Let's pretend this is 1970 and we've got a tape machine. Okay, and then out of the tape machine you might go back to a recording console with all the faders. And then from there you may go to an amplifier and then back to speakers. Okay, microphone, mic preamp, EQ, compressor, tape machine records, plays back into a recording console with faders to mix the sounds, to an amplifier, and then to speakers. Of course, in there somewhere we have to have headphones for the musicians to hear what's going on. So from here we go out to another amplifier and then over to a set of headphones. I mean, I'm just giving you a rough idea of what a block diagram is. That tells you, okay, well, from the microphone, this is where we're going to go and how the signal is going to proceed. Okay, now we're going to look at this kind of drawing a few more times, but in the meantime, this is just to illustrate what a block diagram is. It's sort of this overall picture of what you're doing with the sound and where the signal's going. Let me draw what a schematic might look like. This would be T1, transistor 1, transistor 2, resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, and I could get even fancier than that. So this is more of what a schematic is, detailing how the electronic components inside your computer or your iPhone actually are hooked together, where the electrons flow. You can kind of think of it, one of the examples or parallels that I look at and I think of is like when you go to Google Maps, right, and it shows you the whole United States, and then you zoom in a little bit, and then you get to sort of the block diagram of where the cities are and how the roads connect them. And then you zoom in on Los Angeles and you see a squiggle of all the different roads. That's more like the schematic. So one's more detailed and specific, one is a more general view of where signals flow. We'll mostly deal with block diagrams, but many times you can have a schematic that has a block diagram format. So it'll say, okay, this is what's kind of in this section, then we go to that section, and it's not going to be fully detailed, but it's going to be sort of an understanding of what's happening. Okay, so let's talk about the basic components of electricity. Whether you know it or not, when you work on your computer, you're working with electricity and you're working with voltages and currents and all that kind of stuff. You're charging up your computer, you're working with voltages and currents. So let's talk about the basic components. Some people may know these things, some people may not. Let's talk about some of the basic definitional things that make up basic electronics. Power is one of those things. Power is work over time. It's measured in watts. Your light bulb. 100-watt light bulb, you go home, turn on your lamp, 100-watt light bulb is doing work power by emitting light, and it's taking voltage and current and making power out of it that you can see in terms of light. An amplifier, let's stay in the musical domain for a second, an amplifier has a certain power, and that has to do with how much it can move the speakers and what size speakers it can move and how much work it can do over time to move the cone, which generates an air disturbance, which generates the power in the sound wave. So power is work over time. Voltage is a potential energy in a circuit. I'll get into more detail of explanation. It's a really simple concept. Current is interrelated to voltage, and current is the rate of flow of electrons in a wire. Let's think of one wire, okay? You've got a wire. Think of it as, just for the time being, think of it as a garden hose. You've got water on one side pushing through the hose, right? You turn on the spigot. The pressure that the water is going through the hose with would be similar to what voltage is. How much water actually goes through the hose over time is the rate of flow of the electrons, and that's similar to current. Impedance is another term that we use all the time, and basically it's the opposition to the current flow. There's also another term, which I didn't include on the card, which we'll talk about quite a bit, called resistance. And that sort of says what it does. It resists the current flow. You might say, what's the difference between impedance and resistance? Impedance is the opposition to the current flow and is frequency related. So you have high frequency or low frequency. It changes how much it impedes the flow of the electrons. If you think of our garden hose example, it impedes how much water flows through the hose. Resistance is also that same sort of resistance to water flow, but it's non-frequency related. Power in a circuit is the measure in watts represented by P. There's a couple other ways to represent power, like horsepower, right? You think of your car as horsepower, which is the power of one horse. If you've got, I don't know what's a big engine, 422 horses is a lot of power in a car engine. That can actually be converted into watts, because watts and horsepower are both measures of work, measures of power. In fact, that leads me to a funny story. I used to have a professor when I went to the University of Wisconsin in Madison. I studied electronics and I studied a lot about acoustics and audio circuitry, and he would tell the class, you know, the good students can come over to my house at the end of the semester and hear my stereo. Because he spent his whole life building his stereo. You know, by hand. He built the amplifiers, he soldered the wires, he made the speakers, and he was a little neurotic about it because he was a totally avid audiophile. And I got to go over to his house, and in his living room, which was about half the size of this room, which is maybe 20 by 15, on one side of the room he had 2 columns of speakers, and on each side he had 2 18s, 4 15s, 4 10s, all these speaker sizes, right? 8s, 4s, and 1-inch piezo tweeters. On each side he had as much as you'd see in a concert. And back then we had records and turntables. Does anybody remember vinyl records? His turntable, where the needle would sit in the record and ride on the groove, had to be on another floor of the house because the vibrations would make the needle jump when he started playing it loud. And he would brag that he had a stereo with 5.2 horsepower. That's how he'd tell us how cool it was. And he'd play his stereo and he'd turn it up, into the 1912 overture, with the cannons firing and the whole thing. You could imagine this sort of eccentric professor, right? So he'd start it low and then he'd go, oh, here's where the cannons go. And he'd turn it up and your hair would go back. It's like, felt like you were on the battlefield. But some people actually rate their stereos in horsepower. That, I don't know why that came to mind. We were talking about horsepower. And it was one of the fun experiences in college for me. Because afterwards he served bottles of wine and cheese and it was fun. Anyway, voltage. Voltage is potential energy of an electric circuit measured in volts, represented by V. And I'll get in more detail as to what that actually means, volts, and how it relates to current and resistance. The next one is current, as our main basic important electrical characteristics. We start with power, voltage, current, and resistance. So current is the flow of energy within a circuit measured in amperes, represented by I, amperes or amp. Resistance to the electrical flow of electrons. Something with a measured resistance is called a load on the circuit, and it's measured in ohms and represented by R when you write it. So if I say 1,000 ohms, I'd put a little omega after the 1,000 and represented by R. Now, it kind of makes sense to me a little bit when you think about what electrons do in a wire. They have to flow from atom to atom to atom and move along in the wire. And it needs some sort of energy to push it along. And that would be voltage, pushing the electrons to flow through a wire. And the resistance of the electrons to flow through the wire would be called the resistance. When you have a resistance in a wire and you have electrons flowing, you'll eventually generate some heat, right? Friction of the electrons moving through a wire. Now that's any wire. We always represent wires and cables in the studio as being perfect and no resistance at all, but they all represent some small, minute resistance to the signal flow from one piece of gear to the next. And that's where you get into the monster cables versus not monster cables. And they charge you 3-4 times as much as a regular cable because they've made a cable specialized in trying to minimize the resistance of electron flow by the way that they've internally constructed the cable. I can get very into that, but first we got to get into some more details about electronics. But that's actually sort of an interesting concept because people ask me all the time, is it worth it getting a monster cable? That's sort of a personal judgment. Technically speaking, they have a point of what they're doing is correct, but if you can really hear it, I doubt you can really hear it. Gold is a better conductor than silver, and most wires are made actually out of a tin and aluminum alloy, which is very conductive, but not as good as gold. So if it's more conductive, it has less resistance. Okay, so basic electronics. Impedance is the resistance to flow of energy in a circuit, very similar to resistance, except it has to do with different frequencies being treated a little differently. Capacitors would be considered an impedance source, and inductors, we haven't discussed what they are yet, but there are components that are frequency dependent. And that matters to us because once we transduce a sound from the acoustic domain through a microphone into an electronic signal, it has a spectrum, and that spectrum goes up infinitely. And so the higher frequencies being treated differently, just moving through a cable or through a piece of electronic gear, will actually affect how it sounds at the other end of the chain. So there's a basic law of electronics, very simple interrelationship between these three component values that we use as our basis for electronics: voltage, current, and resistance. So the basic formulas that are kind of important in terms of determining the relationship between voltage, current, and resistance, which kind of makes sense because if you have less resistance in a wire when you're trying to push the same amount of pressure on the electrons, or let's say your water hose, same amount of pressure, except there's less resistance to the water flow, you're going to get more water flowing. If there's more resistance to the water flow because the hose narrows in one area, then you're going to get less water flow with the same amount of pressure. Okay, so the basic law, it's called Ohm's law, and I'll show you how I remember it. It actually is voltage equals current times resistance. I remember it like this. If I wanted to find the voltage, I would multiply the current times resistance. If I wanted to find the resistance, I would take the voltage and divide it by the current. If I want to find the current, I take voltage divided by resistance. Okay, the next law that's important is called Power's law or Watt's law. Power equals voltage times current. And you can make these two formulas interact because we know that voltage is current times resistance. So not that you need to know any math, it's just interesting how these three components sort of react and interact with each other.